Hello, welcome back. We're very pleased to have Sheng Zhang from Jiaotong University, Southwest Jiaotong University, and he's speaking on a submetric characterization of Rolewicz property beta. Sheng?
Okay. Thanks. Very happy to give my first online talk at this Fana Space webinar, and I'm talking about the submetric characterization of Rolewicz property beta. Okay, let's first recall the definition of property beta of Rolewicz. Well, it's actually an asymptotic property of Fana space, and the definition here is an equivalent definition due to Kuzarova in 1991. And the Banach space X is said to have property beta if for every t there exists a delta, so that whenever you have a point in the unit ball of X and a separating sequence Xn, then you can always find one of these Xn, say Xk, so that the distance between X and Xk is strictly less than 2. So it's less or equal than 2 minus 2 delta. And you can similarly define a modulus for property beta, just like the modulus for uniform convexity, well, in this way. And then the space has property beta if and only if the beta modulus is positive for every t. Okay, so maybe we should take a look at this, this picture. It just summarizes the definition of property beta. Now the O is just the origin of the space. And X is just an element in a unit ball. And Xi is a sequence of it's a T separating sequence, meaning that every two of these Xi, their distance is at least T. Then whenever you have this fork configuration, well, because it looks like a fork, right? And this is how they call it. And whenever you have such a fork configuration, you can always find one of these Xi, say Xk, so that the distance between X and Xk is less than expected, strictly less than 2. So this is just the definition of property beta. And this property can be characterized using, in terms of Lipschitz embeddability of Countably branching tree. So the definition of Countably branching tree, well, is just an unweighted tree. And it has a root, which I denoted by the empty set. And each of its vertices has countably many edges indecent to it. So actually, the vertex set of T has a one-to-one correspondence with finite subsets of natural numbers. So each vertex of T can be represented as a finite subset of natural numbers in this way. So N1 to Nk. For example, J is a vertex of T. You can write it as N1 to Nk. And the K here, we say the K here is the length of this vertex or the height of this vertex. Or sometimes it means, well, it means the level of where the vertex sit. Okay. And the max J is just the maximum number in J, it's Nk, and the minimum J is just the minimum number N1. Okay. And you have ancestor to descendant relations in this tree. We say that a vertex I is an ancestor of a vertex J if J extends I. Okay, so if I is M1 to ML and J is N1 to Nk, then we say I is an ancestor of J or J is a descendant of I. If, well, the length of I is strictly less than the length of J, L is less than K. And Mi is equal to Ni for every I between 1 and L. Okay. And the metric on T will be always the shortest path metric on graph. So this, I draw this picture. This is just the countably branching tree. So this is the root. And as you can see, each vertex has countably many descendants. Okay. So this is actually the countably branching tree of level 1, 2, 3, 4, of level 4. Okay. Now, as I mentioned, well, the property beta can be characterized in terms of Lipschitz embeddability of this tree. And let me just recall the Lipschitz embedding is just a one-to-one Lipschitz map, and whose inverse is also Lipschitz. And this theorem, this characterization is due to Boddy, Lancian, and Carton in 2010. And they proved that within the reflexive Banach spaces, property beta can be characterized using Lipschitz embeddability of the Countably branching tree. So more precisely, if X is a reflexive Banach space, then X doesn't have an equivalent norm with property beta if and only if the tree, the Countably branching tree T, admits a Lipschitz embedding into the space. So actually, they proved this theorem using the notion of strengthened index. So what they prove is actually the equivalence between 1 and 3. So the one is that a strengthened index of X is larger than omega, or the strengthened index of the dual space is larger than omega. This is equivalent to of the saying that X doesn't have an equivalent of property beta. Okay, now enough background. Let's get to the topic. So at the beginning, I was wanting to prove some stability result of property beta under nonlinear maps. For example, nonlinear embeddings, nonlinear quotient. So let's take a look at the easiest case, Lipschitz embedding, the stability of property beta under Lipschitz embedding. So suppose X is a Banach space that has an equivalent norm with property beta, and you know there's another Banach space Y admits a Lipschitz embedding into X. Then the conclusion is Y also has an equivalent norm with property beta. And actually, this is not even a proposition, because if you look at the definition of property beta, it's just a one-line proof. Okay. So, but I want to prove this easy proposition using the previous metric characterization, the Baudier, Lancian, and Cartan's characterization. So, how to do that? So first, assume by contradiction that Y doesn't have an equivalent norm with property beta. Suppose Y is not beta renormable. Then you separate it into two cases. Case one is if Y is reflexive, so for reflexive space which doesn't have an equivalent norm with property beta, by this characterization, you know that the Countably branching tree admits a Lipschitz embedding into Y, and hence into X, because Y admits a Lipschitz embedding into X. So the tree actually Lipschitz embed into X, but this is not possible because X has property beta. Okay. Now the other case is Y is non-reflexive. So what if Y is non-reflexive? How can we do that in this case? So for non-reflexive case, we can apply the James characterization of reflexivity. And I think this is a well-known characterization that you can find in any textbook in functional analysis. And so if Y is non-reflexive, then for every theta between 0 and 1, you can find two sequences. The first one is in the unit ball of Y. The other is Yj star in the unit ball of the dual space of Y. So that Ym star Yn is equal to theta for m less or equal than n. And when m larger than n, the quantity is 0. And now you can define a new map from the tree into phi, where it's defined in the following way. For every vertex j, phi j is defined to be the sum of yi, where I, the index I, is taken from j. Of course, now the vertex j is viewed as a finite subset of natural numbers. Okay. And now in the paper of Dealworth, Kuzarova, and Rendriano Rivoni, in the paper, they prove that some stability result of property beta, which I will mention later. And in this paper, they have this lemma. This map, phi, is actually one-to-one map and satisfies two nice properties. The first one is phi. Of course, this phi cannot be a Lipschitz embedding, but the first property of phi is its ancestor to descendant Lipschitz embedding, meaning that you have this Lipschitz embedding inequalities only for those vertices that have this ancestor to descendant relation. Okay, and the second property says that, well, for those vertices that are far apart, so by far apart I mean the maximum number of the first vertex is smaller than the max number of the first vertex is smaller than the minimum number of the second vertex. So whenever you have such vertices, the distance between their images under phi must be separated in some sense. Okay. So these two nice properties that phi satisfies. Okay, so the question is, well, can we map the countably branching tree T into a space with property beta in such a way? So this is the question. And maybe, so at this point, maybe we should look back to see why you cannot embed the tree, embed the countably branching tree into a space with property beta Lipschitzly. So this, I mean, I'm going to recall the proof of non-embeddability of the countably branching tree into a space with property beta. So, and the proof actually relies on the bending lemma, So the bending lemma is like this: if X is the Banach space with property beta, and F is a Lipschitz embedding from the fork into the space X. By the fork, I mean again this picture. This is a fork, but now this point X and Xi are not in the Banach space. This is a graph now. So X is a vertex, O is the branching point, and Xi are tips. And each edge has weight 1, so it's an unweighted graph. So the distance between X and O is 1, and distance between O to each Xi is again 1. Okay. So this is now the fork F is a graph. So whenever you have a Lipschitz embedding from the graph F into a space with property beta, then you can always find one of the tips xk, so that the image between x and xk, the distances must be less than expected, less or equal to 2 times the Lipschitz constant of f times something strictly less than 1. This is 1 minus some beta modulus thing. Okay. So it's less than expected because, well, if you don't have this thing. Actually, fx, the distance between fx and fxk is, of course, by Lipschitz condition of f, is of course less or equal than 2 times Lipschitz constant of f. But now it's less than expected. You have something less than 1 here. And the proof is quite easy. It follows directly from the definition of property beta. So you have these 3 inequalities. The first one is the distance between the image of x and O. Well, by Lipschitz condition, you know that this quantity is less or equal than the Lipschitz constant of f. And the same reason, fxi, the distance between fxi and fxo, fo, the distance between them is again less or equal than Lipschitz constant of f. And the distance between the image of tips should be, the image of tips, they are separated because f is a Lipschitz embedding, right? So you use the other inequalities in the Lipschitz embedding condition. So you get the distance between the image of tips must be, 2 over Lipschitz constant of f inverse. Okay. So now you have this these 3 inequalities, and you apply the definition of property beta, you get this inequality 1. So this is the bending lemma. And now, from this bending lemma, we can prove the non-embeddability of the countably branching tree into the space with property beta. So now, X is a space with property beta, then there's no Lipschitz embedding from the countably branching tree into X. So the proof goes like this. If you have a Lipschitz embedding from the tree into X, for example, let's forget about these words. Let's take a look at this picture again. If you have a Lipschitz embedding from this tree, the tree T, into a space with property beta, then you look at the first 2 levels of the countably branching tree. Okay, so this is the root. And you see that there are countably many forks incident to this root, right? And you apply the bending lemma to the first fork. So you find a red point located on the second floor, so that using the bending lemma, so that the distance between the image of these 2 red points is less than expected. Okay, and then you apply the bending lemma to the second fork, you get another red point, and then you do this. You just do this and do this procedure, and you get a sequence of red points located on the second floor. Okay, and then for each red point on the second floor, you see there are again countably many forks incident to it, and you do the same thing. Okay, so finally you get a collection of red points, and which forms a subset of the tree T. And this subset is actually, well, this subset consists of red points. And this subset is actually two isometric subset of T, meaning that this subset is isometric to the whole tree T up to constant 2. Okay, but when you restrict the Lipschitz embedding to this subset, the Lipschitz constant actually becomes smaller because remember how we choose these red points, the distance between their images are less than expected. So the Lipschitz constant becomes smaller. Okay, let's go. So you get a subset T1, which is 2 isometric to the whole tree. So that when you restrict the Lipschitz embedding to T1, the Lipschitz constant is less than expected, less than some tau. Well, at the beginning, I can assume that the Lipschitz constant of f of the embedding is 1. And then the restriction of this f, the Lipschitz constant, is less than tau, where tau is something strictly less than 1 minus this beta modular thing. Okay, so you do this procedure once, you get tau. You do it twice, you get tau squared. So you repeat this procedure n times, you get the Lipschitz constant of f. Some restriction of f is less or equal than tau to the n for every n. But actually, tau to the n should be at least 1 over Lipschitz constant of f inverse because f is Lipschitz embedding. And you get a contradiction by n tends to infinity because tau is by the beta modulus, and tau should be less than 1. So when n tends to infinity, you get 0 on the right side. Okay, this is the proof of non-embeddability of the countably branching tree into a space with property beta. And as you can see, the key point is the bending lemma, right? And in order to prove this bending lemma, all we need is these 3 inequalities. Okay, the 3 inequalities, let's go back and check it. The first 2 inequalities only require the f to be Lipschitz, right? We only use the Lipschitz condition in the first 2 inequalities. And the second inequality says that, let me repeat it again. The third inequality says that the images between tips are separated. So let's go back and check if the phi in the non-reflexive case satisfy these 2 properties. So phi has these 2 nice properties. One is ancestor to descendant Lipschitz embedding. And this property actually assures that phi must be Lipschitz. Okay. And the second inequality only says that those vertices that are far apart, their images are separated. Okay. So tips in the tree are not necessarily far apart. When you do the self-improvement argument, the tips in the trees are not necessarily far apart. So phi actually doesn't satisfy the third inequality. But it's okay, I think. Actually, we can prune a tree to make all the tips far apart. I mean this lemma. So the lemma is just it just says that I can prune a tree. I can find isometric subset of the countably branching tree so that each vertex is of the same height, they are far apart. So more precisely, I can find a sequence Tn of the countably branching tree so that the sequence is decreasing and each Tn is isometric to T up to some constant 2 to the n. Okay. And the third condition is the far apart condition. And it says that for every vertex j in Tn, and j, well, let's denote the immediate descendant of j in Tn by j union ji. So note that these are immediate descendant of j in Tn, not in T. So each ji has length 2 to the n. So whenever you have this immediate descendant, j union ji, these immediate descendants must be far apart in the sense that max ji is smaller than the minimum ji plus 1 for every I. Okay, so the proof, well, this is actually not a difficult lemma. It's actually very easy, but the proof use the induction. T0 is just the whole tree T. And if Tn has been defined, then I would define Tn plus 1 as follows. First, I'll choose the root, the empty set. So we'll forget about this word. We should go back to take a look at this tree. Okay, so suppose Tn has been chosen, and I would define Tn plus 1. Okay, first I would choose the empty set, the root. And suppose a vertex in Tn has been chosen. For example, this vertex is J in Tn has been chosen. Now you look at the next level of J. The vertex here. These are immediate descendants of J in Tn, and you look at the first immediate descendant, and you pick, well, an immediate descendant of this point, this vertex, and I mark it as red point. So the first step is just you choose an arbitrary grandchild of J. Okay. Now, since the immediate descendant of J, they must be far apart by induction hypothesis, meaning that these vertices must be far apart. So you can find one of it, for example, this one, so that the minimum number of these vertices is large than the maximum number of the red point you have just chosen. Okay, and then you choose arbitrarily an immediate descendant of this vertex, and you mark it as the second red point. And you keep doing this, and you get a sequence of red point located on the next two levels of J. Okay, so this procedure tells you how to choose descendant of J in Tn. So in this induction process, you get a collection of red points, which is a subset of Tn, and these red points actually forms the vertex set of Tn plus 1. So maybe I didn't explain it very clear, but if you build a sequence Tn by hand, you actually find it. This is actually super easy. For example, I will show you how to build T1 from T0. Okay, T0 is just the whole tree T. Okay, so first I would choose the root empty set, and then I start from the second level of the tree, and I pick the vertex 1, 2, 3, 4, 5, 6, 7, 8. So I pick the vertices in this way, so that these vertices are of course a descendant of the root, and these vertices they are far apart, right? The max number of the first vertex is smaller than the minimum of the second, right? And now you look at the vertex 1, 2. Again, you want to choose descendants of 1, 2 located on the fourth floor, and you choose its immediate descendant as 1, 2, 3, 4, 1, 2, 5, 6, 1, 2, 7, 8, and so forth. Okay, then these descendants of 1, 2, they are far apart. And again, you do the same thing for the vertex 3, 4. You do the same thing for the vertex 5, 6. So you get an 2 isometric subset of T, which I denoted by T1, so that vertices of the same level, they must be far apart. Okay, so this is how you build T1 from T0, and you can similarly build T2, T3, and you get a sequence Tn. Okay, so this is the idea. So now actually we already have a metric characterization of property beta. I don't know if you noticed that, but if you don't, let me just state the theorem and reprove it. Okay, so X now is a Banach space. Then the following are equivalent. X doesn't have an equivalent norm with property beta if and only if there's a Lipschitz map from the Countably branching tree into the space X, so that, well, it satisfies the following properties. Whenever you have whenever you have a vertex in T, and J, but the vertex is denoted by J, and J1 bar, J2 bar are descendants of J in T, so that these two descendants are far apart, then the distance between their images must be, well, separated. It can be controlled from below. So the item 2 of this theorem says that the item 2 of the vertex says that actually phi maps those vertices of the same height to a far apart set, something like And the proof actually is the combination of what I said 10 minutes ago. Okay. One implies two. One implies two. When X doesn't have an equivalent norm with property beta, then you can separate it into two cases. Case one is if X is reflexive, then you use Baudier, Lancian, and Cartan's characterization. You know the Countably branching tree, Lipschitz embed into X, and of course, a Lipschitz embedding satisfy item 2. So if X is non-reflexive, then you use lemma. You use the James characterization of reflexivity. You define the phi as before, and phi, remember the phi, which is this. Where is it? Okay, this one. You define the phi like this, and of course, phi satisfy item 2, because why? First is ancestor to descendant Lipschitz embedding. So it's Lipschitz, and it has this nice property that it maps vertices that are far apart. Their images must be separated. Okay, so this is 1 implies 2. And for 2 implies 1, use the self-improvement argument, as I said. Sorry. For 2 implies 1, we use the self-improvement argument. Suppose, well, by contradiction, X has an equivalent norm with property beta, and you can find a phi, a Lipschitz map phi from the Countably branching tree into X that satisfy 2. So then by bending lemma, you can find a sequence of Tn, as I mentioned in lemma. Well, I think I forgot to mention this Tn in the previous lemma are called Pruned isometric subset of T. You can find a sequence Tn so that if you restrict this phi to Tn, its Lipschitz constant is smaller. It's actually at most tau to the n. Again, tau here is something less than 1. Okay, and since tau to the n must be at least gamma. Well, now what is gamma? Gamma is this here, because, well, you know that from this item 2 that vertices of the same height, vertices of the same height, if they are far apart, then their images, the distance between their images must be controlled from below. It's larger, it's at least constant times the distance between J1 bar and J2 bar. So the Lipschitz constant is actually at least gamma. Okay. So again, you let n tends to infinity, you get a contradiction. So the proof, well, how to choose this Tn is the key point. How to choose this Tn? Actually, it's I've mentioned it before. It's again this picture. You use the induction. Suppose Tn has been defined. How to define Tn plus 1? Okay. So if J in Tn has been chosen, again this vertex I denoted by J. Okay. Suppose this vertex has been chosen in Tn, then you see there are countably many forks in descent to this vertex J. And you look at the first fork here, and you use the bending lemma to find the red point located on the next 2 levels of J. You can use the bending lemma because the phi satisfy the property. Because the phi satisfy the property, first one is Lipschitz, and the second one, it has this nice, well, just every time I have to say this, it maps vertices that are far apart. So vertices that are far apart has separating images. So phi has this nice property so that you can apply the bending lemma to the first fork to get a red point. Again, you can apply the and again, sorry, since the immediate descendants of J, now at this point, this vertex is J, if you remember. So the immediate descendant of J must be far apart by induction hypothesis. So you can actually find one of them so that, for example, this point, so that this point, the minimum number of this vertex is larger than the maximum number of the red point you have just chosen. So again, you use the bending lemma to this fork, and you find the second red point. So you do this procedure again, you find a collection of red point which forms a 2 isometric subset of Tn, and it's actually Tn plus 1. And the Tn plus 1 satisfies each, well, red points of the same level. They must be far apart. Okay, this is how you choose it. How you choose Tn. And since, well, you use the bending lemma here, the distance between the image of the red points must be smaller than expected. So when you restricted the phi to Tn, the Lipschitz constant of phi is getting smaller and smaller. It's just like the proof in the non-embeddability of the Countably branching tree into the space with property beta. Okay, so actually it follows the same idea. Okay, so so actually this metric characterization, well, this version is not the original one that I obtained. After I obtained my version, I had to talk with I had discussion with Florent Baudet and Chris Garland, and they told me that actually my characterization can be improved. And actually, if you take a look at this item 2, this condition here is actually hidden in the lemma of Dilworth, Kruzarova, and Redriano-Rimoni. I mean this lemma. This lemma, right? The condition 2 is actually hidden in this lemma. And in this paper, they actually prove that the property beta is stable on the uniform quotient. And they use, I believe they use this lemma, and then they also prove that such a map, you cannot map the Countably branching tree into a space with property beta in such a way. I believe they also prove this, but they use different approach. They use a complicated fork argument, and also they introduce some kind of diamond type graphs. Okay, so the approach is different from this. Okay, so this is the metric characterization. And actually, this type of metric characterization is different from those ones that we usually see. I mean, those ones in terms of Lipschitz embeddability of a certain graphs. So in terms of, in language of Ostrovsky, this type of metric characterization is actually called submetric characterization. So let me recall the definition of submetric characterization. So we say a metric space T is a submetric test space for a class P of Banach spaces if the following two items are equivalent. First, a Banach space doesn't lies in this class P. Second, there exists a Lipschitz embedding. Sorry, there exists a partial Lipschitz embedding from T into X. By partial Lipschitz embedding, it means that, well, the F satisfies this Lipschitz embedding inequalities only for certain pairs of X, Y in T. Well, this inequality only holds for X, Y in certain subset S of T times T. So this is the definition of a submetric characterization. And actually, if you look back our metric characterization, this phi in item 2, actually, it is a partial Lipschitz embedding, right? Okay. So that's why we call it a submetric characterization. Okay, now we can go back to the stability of property beta on the nonlinear maps. So now this time I think I should go further to consider the stability of property beta on the Coarse Lipschitz embedding. So let me recall some basic definitions. If you have a map between metric space, then you can define the Lipschitz constant of this map when distance is the least d, and I denote it by lib d. Okay. And we say f is Lipschitz for large distances if lib d is finite for every d. And we say f is Coarse Lipschitz if one of these lib d is finite. And we say f is Coarse Lipschitz embedding if you can find a non-negative d and a be positive, so that you have this Lipschitz embedding condition only for distance larger than d. Okay, so this Coarse Lipschitz embedding is actually a special type of partial Lipschitz embedding in language of Ostrovsky. Okay, so now the stability of property beta under Coarse Lipschitz embedding. This theorem first appears in Baudet, Cartan, and Lancien's paper. And if X is a space if X is a Banach space with that has an equivalent norm with property beta, and Y, another Banach space, admits a Coarse Lipschitz embedding into X, then Y also has an equivalent norm with property beta. So property beta is stable under Coarse Lipschitz embedding. So the proof using our metric characterization, you can assume first, sorry, if y doesn't have an equivalent norm with probably beta, then using our metric characterization, you can find a partial Lipschitz embedding phi from the countably branching tree into y. Well, remember phi satisfies two properties. The first one is phi is Lipschitz, and the second one, the vertices that are far apart, their images must be separated. Phi has these two nice properties. Okay, and you can denote the Coarse-Lipschitz embedding from y to x by f. Okay, so now if you compose phi with f, you get a map from t into x, but the map is not necessarily a partial Lip embedding. That satisfies item 2 in the metric characterization theorem, because, well, let's assume, suppose if f is a Lipschitz embedding, then the composition phi and f must be a partial Lipschitz embedding, which satisfies item 2 in the theorem. But this is not possible because x is probably beta. But now f is only a coarse Lipschitz embedding. It's not a Lipschitz embedding. It is a Lipschitz embedding when distance is larger than some d. So I want distance to larger than some d. So what I do is I consider the restriction of this phi, of this partial Lipschitz embedding. I consider the restriction of this phi to some Pruned isometric subset of t, the tk, if you remember. So the tk is actually it's isometric to t, and the distance in tk is at least 2 to the k. So if you choose large k, and you consider the composition of the restriction of phi and f, this composition is actually, again, a partial Lipschitz embedding, which satisfies 2 in the theorem. And now by the characterization, this is not possible because x has an equivalent norm of probably beta. So this is the idea of how to prove this theorem. Okay. So now let's go a little bit further. So how much time do I have? Okay. So now let's go a little bit further. The stability of probably beta under nonlinear quotient. So I should recall the definition of nonlinear quotients. A map, again, a map between metric spaces, it's called co-uniformly continuous if for every d there's delta, so that the image of, so that for every x in the domain space, the image of the ball centered at d with radius centered at the x with radius d, the image of this ball contains fx as an interior point. So it contains the ball with center fx and radius delta. So this is actually the generalization of open mapping, a linear open mapping in the Banach space. So if the delta can be chosen as a multiple of d, then we say such a map F to be Co-Lipschitz. And now a Lipschitz quotient map is just a Lipschitz map, which is also Co-Lipschitz. And a uniform quotient map is just co-uniformly continuous plus a uniformly continuous. So this is a definition dates back to 1999 by Bates, Johnson, Linden, Strauss, Price, and Sheckler. Okay, and then the coarse quotient map, the definition of this coarse quotient map is a bit tricky. We say the F is a co-causally continuous if there is a constant k, non-negative, so that for every distance larger than k, there exists a delta again. So that for every x, the ball in y centered at fx with radius d is contained in the k neighborhood of the image of the ball with centered x, radius delta. Okay, so for coarse quotient, the definition of coarse quotient is just, again, similarly, causally continuous plus co-causally continuous. And here, the k neighborhood of set A is just the union of all closed balls, with radius k, where the center taken from set A. Okay. So if you are not familiar with these notions, it's okay. because we have this Co-Lipschitz for large distances property. We know that, I think it's well known that uniformly continuous maps and coarsely continuous maps, they must be Lipschitz for large distances if the domain space is metrically convex. So we have similar properties for co-uniformly continuous maps and co-coarsely continuous maps. But this time you require the target space Y to be metrically convex. So now you have a map from a metric space X to a metrically convex metric space Y. Now first, if F is co-uniformly continuous, then for every D positive, there exists a C only related to D. So that F satisfies this Co-Lipschitz condition only when distance is larger than D. So that only when radius R is larger than D. Okay, so these co-uniformly continuous maps are actually Co-Lipschitz when distances are large. Okay. And for co-coarsely continuous map, if F is co-coarsely continuous, then you have this K, non-negative, so that for every distance larger than K, you can find a constant C only related to D, so that it also satisfies this Co-Lipschitz condition, but now you have the K here. So that's the difference between co-uniformly continuous and co-coarsely continuous. In the coarse case, you cannot get rid of this K. So in view of these two, Co-Lipschitz for large distances property, we can actually unify these two notions in just one framework. I mean, I can unify the notion of co-uniformly continuous maps and co-coarsely continuous maps. Of course, when the target space Y is metrically convex. So now X and Y be two metric spaces, and F is a map between them. Okay, and F is either uniformly continuous or co-coarsely continuous. Now, suppose the target space Y is metrically convex, then there exists two positive number K and C, so that F satisfies this Co-Lipschitz condition, but still you have a K here. Okay, so this corollary I think is nice. So it actually unifies the two notions when the target space is metrically convex. So next, sorry. So next time when you want to prove something about uniform quotient, remember to use this corollary, and you get similar things for coarse quotient. Okay, so the theorem is like this. The theorem is about stability of property beta under uniform or coarse quotient. And the uniform quotient, the stability of property beta under uniform quotient, as I mentioned, this theorem is due to Dilworth, Kuzarova, and Rendry and Rimoni. And what I prove is the coarse version. But actually, since these two notions can be unified, so I just put them together. So X is a Banach space that is beta renormable, and Y is a uniform or coarse quotient of a subset of X. Then, and the quotient map must be Lipschitz for large distances. Then Y is also beta renormable. Okay, so the Lipschitz for large distances property for the quotient map is necessary. Without this condition, the theorem is not true. There are counterexamples. So the proof of the is the same idea as that in the Coarse-Lipschitz embedding. Okay, so again, you assume that Y doesn't have an equivalent property beta, and you use the metric characterization theorem, you find a partial Lipschitz embedding phi from the Countably branching tree into Y. Okay, and for simplicity, I would denote the image of every vertex J to be Vj. Okay, so let's forget about this and take a look at this picture. Okay, this picture actually summarizes the proof. X is a beta space. It's a space with property that has an equivalent norm with property beta, and X has a subset S. And Y is another Banach space. And from the subset S to Y, you have a quotient map. This quotient map F I denote it by F. This quotient map is either a uniform quotient or coarse quotient. Now I want to prove that the space Y is also beta renormable. So I assume this is not a case. So use the metric characterization theorem, you can have a partial Lipschitz embedding from T into Y, okay? And for every vertex J, you denote the image of phi J to be Vj. Okay, so now for every J, for every vertex J, actually I can use the quotient map F to find Uj in S, so that Fuj, the distance between Fuj and Vj is at most some constant K. Okay, so I can pull back, how do I get this Uj? I can pull back this Vj back into the subset S using this quotient map. So if the quotient map, if F is a uniform quotient, then we know that the uniform quotient onto a Banach space must be surjective. So when you pull back, you just choose the preimage of Vj under F. But if F is a coarse quotient map, of course, a coarse quotient map is not necessarily surjective. So all you can do is find some Uj in S so that the distance between Vj and Fuj is at most some constant K. So now this actually, sorry, I have some problem with my throat. So this actually defines a map from T into X, from this J to Uj, okay? So this actually defines a map. And this map, you can check. It is a partial Lipschitz embedding. But again, since you have this K here, you have to consider the restriction of phi to some Pruned isometric subset of T when you choose this n large and you consider the restriction, if you take this n large, then the K can be ignored and the composition of the restriction and this pullback will be a partial Lipschitz embedding from the tree into the space X. But this is not possible because the theorem tells us the X has a property beta and there's no such map into X. Okay, so this is the idea of proof, and I hope I explained it in a clear way. Okay, I think I should stop here.
Okay, thank you so much, Sheng. And we also appreciated the calligraphy on that picture. Any questions?
Yes, one question maybe, which might actually already be known. I'm not absolutely sure. You will tell me certainly. If you take a reflexive space whose Schlenk index is omega 0, or if you wish, which has an equivalent asymptotically uniformly smooth norm, and another space which calls Lipschitz embed into that space, do you have the same property? That is the Schlenk index omega 0 for the space itself in the reflexive case stable under Coarse-Lipschitz embedding?
I don't know this problem. I think it's open, right? I don't know.
Okay, it's an exciting question in the direction of
yes, I know. Actually, I was thinking about a similar question about the stability of AUS, the asymptotic uniformly smooth space, under Lipschitz quotient. It's, I think, under nonlinear quotient maps, and I think it's hard because C0 has AUS. That's the problem, right? Every separable space in that C0 Lipschitzly in a Lipschitz. So I think that's the. I don't know if you want some kind of characterization. At least the graph cannot be separable. So that means you have to put some weight on each edge, I think so.
Incidentally, another question crossed my mind after what you said. To the best of my knowledge, it is not known if the collection of quotient spaces of C0 is stable under Lipschitz isomorphism. For subspaces, it is known to be true, and for quotient, it is known with an extra technical condition that is assuming beforehand that the dual has the approximation property, which looks like a strange abstraction, but in full generality, it is open and it could be a question maybe for PhD students. But there is one technical abstraction, unless it has been solved very recently, but for showing that quotient of C0 is stable under Lipschitz isomorphism as a collection of spaces.
Can you repeat the question? I didn't follow.
Okay, let me, I'm sorry to take so long. Take X, a quotient of C0, of the usual separable C0, and Y be Lipschitz isomorphic to X.
A quotient of C0.
That Y is linearly isomorphic to a quotient of C0.
I don't.
It's nearly showed, but you need to assume approximation property of the dual space, which is a strange technical restriction. So I think it is safe to conjecture that this is true, but it is not shown so far. Okay, this was shown by a PhD student of mine called Dutrieux in a few years ago. Florent knows this extremely well, of course. Okay, thank you again. Sorry for having been so long. Thank you.
Thank you.
Any others? Gilles, you mentioned that there was some obstruction recently solved in like some technical thing. What was that you were referring to?
Which one?
No, the abstraction, I mean, I did not express myself properly. For showing the stability of the collection of quotients of C0 under Lipschitz isomorphism, there is one linear lemma which requests to assume beforehand that the dual of your spaces has the approximation property. And then, if I remember properly the lemma, it is to say that a quotient of C0 whose dual has the approximation property is a linear quotient of a C0 sum of a sequence of its finite dimensional linear quotients. I mean, it's a pretty involved lemma. But without approximation properties, this part fails. And I don't know about any way to get around it.
Okay.
That's all what I know on this.
Thank you.
You're welcome.
Of course, if it's not true, it's maybe even more interesting.
Yes, that would be extremely exciting if not true. But if I have a bet to take,
right?
Well, I believe it's true. If it's not, please let me know. I mean, I will enjoy very much a counterexample.
But proving it requires some kind of a new idea, for sure. Yeah.
Mm-hmm. Yes, but you know this abstraction very well. I mean, we had talked about it years ago, and as far as I know, the problem did not move in the last few years, but it's still there. I mean, there are versions for LP spaces, little LP spaces, which are shown to be true, but in the C0 case, there is this strange obstruction which still holds. I mean, if anyone has questions about it, please address Bill Johnson. Okay, he is a reference.
So the approximation property was used to write it as like a C0 FDD. Is that what you said? The space. Like, how was the approximation property used in this?
Well, I would need to gather my thoughts about it, but the one lemma which is in a paper with Nigel, Daniel Lee, and myself, a paper on the subspaces of capital L1 actually is the following. Again, if you have, I hope I will reproduce it properly. If you have a quotient of C0 whose dual space has approximation property, call it X, then there is a sequence En of quotients of X, so that X is quotient of the C0 sums of the En. You know, so that's, again, there are many arrows, it's a little bit tricky, but this lemma is used with result about now the nonlinear part is involving finite dimensional spaces. I mean, but then I will need to do my homework before saying more, because I don't have this part in mind at this moment.
Well, to make it a little bit simpler, assume that the quotient of C0 has its dual space having an FDD. Then this means that the quotient is just the C0 sum of finite dimensional quotients of C0. And you can do it there. And then you can eliminate the dual having, you can change the dual having an FDD to the dual having the AP, because this makes it complemented in such a space, and do it like that. Mm-hmm. So you can do it, you can break it and make one intermediate step to make it look a little simpler, but it's still, but this is very much connected to the approximation property. So without the approximation property, presumably what you have to do is work with Markushevich bases for this quotient. And then there are techniques that have been developed since then that help a little bit, but it's still doesn't give a solution.
Okay, okay. Okay, thank you. Thank you, Bill, for all of these enlightening comments.
Okay, are there any questions for Sheng? If not, thank you so much again.
Maybe I have a remark if you
sure,
still have time.
Go ahead, Jill. Yeah.
Hi, Sheng. Thanks very much for this very nice talk. So what I wanted to mention is that not having an equivalent norm with property beta does not imply the Lipschitz embeddability of the tree. This makes your result even more interesting. And this fact, this remark that I mentioned is due to Yoel Perrault, who showed that the trees do not Lipschitz embed into James space, for instance. So James is not reflexive, it phase beta, but still you cannot embed the trees.
So you cannot embed a tree, actually, I read the paper before, you cannot embed a tree into quasi-reflexive space.
Right, into a quasi-reflexive with Schenck index omega, and the dual has Schenck index omega. So that makes your result even more interesting. You need to go to a partial embedding. Okay.
Thanks. Thank you.
Thank you.